This video is part 3 of a set of videos covering section 3.1 on the chain rule. In this video, we're going to continue practicing a few more versions of these basic chain rules using these alternate explanation forms rather than the more traditional form. And then we'll also see taking derivatives of a chain rule within a chain rule. So a function, a multiple composite function, right? An f of g of h of x, right? A three-part so-called chain rule. All right, so up first, let's take a look at the derivative of secant of x cubed. Again, this is the derivative of secant of a function. So our chain rule says we're going to take the derivative of secant of a function. The answer will be secant of the function, tangent of the function, times the derivative of the function. And in this case, our function is x cubed. G of x is x cubed. So the derivative of x cubed is 3x squared. All right, so derivative of secant of a function, secant function, tangent function, times the derivative of a function. We plug all that stuff in. And then, again, we can simplify this a little bit by pulling the 3x squared out in front and at least dropping one of the sets of parentheses. All right, how about taking the derivative of e to the tangent x? This is the derivative of e to a function. We've done a few of these. This is our first function that is in the exponent there that is not a polynomial, right? I can take the derivative of e to any function, and tangent x is a function, so derivative of e to the x will be e to the x times, derivative of e to the x is e to the x, but derivative of e to a function is e to the function times the derivative of the function. And in this case, our function is tangent x, and the derivative of tangent x is secant squared x. So plugging into our formula, I get the derivative of e to the tangent x is e to the tangent x times secant squared x. No real simplification or rewrite is really viable here. If I put the secant squared x out in front, I still need the set of parentheses. So not really any good cleanup here that can be done. So we'll kind of leave it alone. Now, I just want to point out, right, it does matter, right? E to the tangent x is going to be something different, obviously, than tangent of e to the x. At least I hope it's obvious that these will be different. Right? In this case, I'm taking the derivative of tangent of a function. And by my rule, right, the derivative of tangent x is secant squared x. So the derivative of tangent of a function is secant squared of the function times the derivative of the function. And in this case, my function, right, tangent of a function, my function is e to the x. Derivative of e to the x is e to the x. Plugging these into my formulas, right, derivative of tangent of e to the x is secant squared of e to the x times the derivative of e to the x, which is e to the x. And this one I can rearrange. I could put the e to the x out in front. Don't have to, but I could. A little cleaner that way. All right, and notice, right, the derivative of e to the tangent x and tangent of e to the x, right, they are different things, for sure. So it matters which thing you're calling g, right? It matters what this inside function is. Even though they're kind of composed of the same types of pieces, it matters which one's which. All right, now, how about these multiple composite functions? What do they look like? Well, how about something that's very similar to what we just did, but now I'm going to take the derivative of tangent of e to the x squared. So I'm taking the derivative of tangent of a function. So I'll need that same rule. But when I go to take the derivative of g, right, this is e to a function. So that itself needs a chain rule, right? So derivative of tangent of a function is secant squared of the function times the derivative of the function, where g of x is e to the x squared. So g prime needs its own chain rule. Now, we found that in an earlier example, either in the part 1 or part 2 of these videos, right? We saw that the derivative of e to the x squared, right? Derivative of e to a function is e to the function times the derivative of the function. So it's e to the x squared times the derivative of x squared, which is 2x. So the derivative of e to the x squared is 2x times e to the x squared, right? We saw that in an earlier example. Now that we remember that, right, now we can just plug in, right? I know what g is, I know what g prime is, so the derivative of tangent of e to the x squared is secant squared of e to the x squared, then times the derivative of e to the x squared, which is 2x e to the x squared. And again, I'm going to throw the 2x e to the x squared out in front. You don't necessarily have to, just kind of looks a little nicer that way. Right, so we can nest these chain rules together, right? We can do a chain rule inside a chain rule. Maybe see one more example of this. So in this case, I want to take the derivative of cotangent of cosine of 2x. Right? So just kind of working from the outside in, right? The derivative of cotangent of a function. Derivative of cotangent of a function requires a chain rule. Derivative of cotangent of a function will be minus cosecant squared of the function times the derivative of the function. Now the function is cosine of 2x. That itself is cosine of a function. So when I take the derivative of cosine of 2x, it also needs a chain rule. So let's take a look at it, right? So start again from the outside in. The derivative of cotangent of a function is minus cosecant squared of that function times the derivative of that function. All right, g of x is cosine 2x. G prime of x, right, needs its own chain rule. So I kind of did this down here, right? The derivative of cosine of a function. Now, since I've used g, I'm going to use h. Right, so the derivative of cosine of a function is minus sine of the function times the derivative of the function. And h of x, right, h of x is 2x, right? I'm taking the derivative of cosine 2x. H of x is 2x. H prime, therefore, is 2. So the derivative of cosine 2x is minus sine 2x times 2, or pulling the 2 out in front, I get minus 2 sine 2x. All right, again, derivative of cosine 2x is minus sine 2x times 2, derivative of 2x. So minus sine 2x times 2 is minus 2 sine 2x. And again, now that I have my pieces, right, now that I know what g is and g prime, I can go back to my original one, the derivative of cotangent of cosine 2x. The derivative of cotangent of a function is minus cosecant squared of that function times the derivative of that function. And I can plug in my pieces. So derivative of cotangent of cosine of 2x is minus cosecant squared of cosine of 2x times the derivative of cosine of 2x, which is minus 2 sine 2x. And again, these can be cleaned up a little bit, right? I can pull the minus 2 sine 2x out in front here, and minus times a minus, right? There's some things I can do. I don't necessarily have to do all of it, but certainly a minus times a minus I'll clean up, and I can pull the 2 out in front. Anything that make it look a little bit neater than what it was is always a nice thing to do. All right, but nesting these rules, right? We've seen combinations of product and chain. We can do chain within chain. We can do chain within quotient and quotient within chain. We could nest all these rules together. Just my advice is take them piece by piece, break them down like we did here. Look at the derivative of cotangent of a function, and don't worry about what that is until it comes time to take its derivative, right? The derivative of cotangent of a function is minus cosecant squared of a function times the derivative of whatever that function is, and go use whatever rule is needed to find that derivative. In this case, I needed another chain rule, but if it needed a product rule or a quotient rule, you go and use those and just kind of take it piece by piece by piece.